Now in this session we are going to see the Material Science Module 5, where we see Clausius-Mosotti equation and applications of dielectrics. Now we see Clausius-Mosotti equation. Consider a solid dielectric material of dielectric constant epsilon r. Let there be n atoms per unit volume and mu be the atomic dipole moment. If alpha E is the electronic polarizability and Ei is the internal field, then we have seen in the previous sessions atomic dipole moment mu is given by alpha E into Ei, where alpha E is the electronic polarization. Now we take this as equation 1. If P is the electric dipole moment per unit volume known as polarization and is given by P is equal to n alpha E into Ei, and let us name it as equation 2. Now rearranging the Ei from the equation 2, we get Ei is equal to P by n alpha E. Let us take this as equation 3. Now by the definition of the polarization P, it can be shown that P is equal to epsilon naught E into epsilon r minus 1. This equation we have seen right from the day 1 of dielectrics, where I have explained what exactly this equation states. So using that equation, we are rearranging the terms in this equation. So we are getting E is equal to P by epsilon naught into epsilon r minus 1. Let us name it as equation 4. Now we also know that the internal field Ei is equal to E plus gamma into P by epsilon naught. This equation we have derived in the previous sessions for the internal fields. So this is also called as Lorentz field. So Ei is equal to E plus gamma into P by epsilon naught. Substitute equation 3 and 4 in equation 5. What is equation 3 and 4 is nothing but equation 3 is Ei is equal to P by n alpha E, and 4 we got it as E is equal to P by epsilon naught into epsilon r minus 1. So substituting the values of Ei and E into this equation 5 of internal fields, we are getting P by n alpha E is equal to P by epsilon naught into epsilon r minus 1 plus gamma into P by epsilon naught. Here, since LHS and RHS is having P, that P can be taken away, cancelled, and you will be getting the equation as 1 by n alpha E is equal to 1 by epsilon naught into 1 by epsilon r minus 1 plus gamma. So the internal fields at an atom in a cubic crystal structure, gamma is taken as 1 by 3, is in the form of. In the previous section, when we are seeing the expression for the internal field, we have given as gamma as 1 by 3 for cubic structure. So here we are taking the same value, gamma is equal to 1 by 3, and substituting the value of 1 by 3 into the above equation, we rewrite the equation as 1 by n alpha E is equal to 1 by epsilon naught into 1 by epsilon r minus 1 plus 1 by 3. Taking the LCM and rearranging and simplifying, you will be getting epsilon naught by n alpha E is equal to epsilon r plus 2 by 3 into epsilon r minus 1. Just rearrange the terms from the denominator to numerator and numerator to denominator, cross multiplying. You will be getting the equation as epsilon r minus 1 by epsilon r plus 2 is equal to n alpha E by 3 epsilon naught. Is the Clausius-Mosotti equation. This is the Clausius-Mosotti equation. It is named as Clausius-Mosotti because these two scientists have given out this relation. So this relation is taken as Clausius-Mosotti equation. Next we see the dielectric materials. What are dielectric materials? And there are, as I said you before, there are 3 types of dielectric materials: solid dielectrics, liquid dielectrics and gaseous dielectrics. Now we see what exactly is the dielectric materials. Dielectric materials are mainly used as insulating materials and to store the electrical charges in a capacitor. So we know that the dielectrics can be used as a material to store the charges which is used in the capacitors. The dielectrics must be having a high resistivity, high or low dielectric constant, low dielectric loss, adequate chemical stability, high moisture resistance and suitable mechanical properties. So for a good dielectrics, you should have a high resistivity. The dielectric constant can be low or high depending upon the usage, and it should have a low dielectric loss and adequate chemical stability, high moisture resistance and having a suitable mechanical properties. Now dielectrics may be solids, liquids or gases. We see solid dielectrics. Solid dielectrics are used as dielectric materials in a capacitor for storing electrical charges. That is, in a capacitor between the two parallel plate capacitors, these solid dielectrics like mica, ceramics can be used, and that is a solid dielectrics. So these are used in the capacitors for storing electrical charges. Jacketing on a conductor for insulation like polyethylene, PVC, natural and synthetic rubber on a conductor in power cables. You all know that in a physics lab you can see a conducting wire over which there is an insulation. That insulation is nothing but a solid dielectric material. Next, quartz crystal is also used as a ultrasonic transducer, crystal oscillator and filters, etc. Next we see the liquid dielectrics, which are nothing but LDs. Liquid dielectrics are used as cooling medium in transformers and some electronic equipments. What does liquid dielectrics do is, it is like a liquid material which when it is passed through it, it becomes cool. That means transformers, when they are heated up, if this liquid material is allowed to it, that cooling effect has been the dielectric is taken away, the heat will be taken away by the liquid dielectric, thereby it becomes cool and transformer will be maintained at a normal temperature. Liquid dielectrics provides suitable insulation between the parts carrying voltage and grounded containers in the transformers. So liquid dielectrics are used as filling mediums in a capacitors and bushings. So in the capacitors we have seen the solid dielectrics like mica or ceramic. Now even liquid dielectrics can be used as a filling medium in the capacitors. Next is a gaseous dielectrics. A dielectric gas is an insulating gas. It is a dielectric material in a gaseous state. So gaseous dielectric are nothing but dielectric materials in gaseous states which can prevent electrical discharge. For example, dry air, sulfur hexafluoride and N2. These are the examples of gaseous dielectrics. Air is used as arc extinguishing medium. Compressed air is used as dielectric insulation in air blast circuit breakers. So gaseous dielectrics are nothing but the insulating gases which do not conduct any electricity. Next is applications of dielectrics in transformers. So till now we have seen there are three types: solids, liquids and gaseous dielectrics, and we have seen the usage and they are used in multiple areas. Now we see the applications of dielectrics in transformers. Transformer oil is a special mineral oil with high dielectric strength used for insulation and cooling of transformers. So it is a type of a special mineral oil with high dielectric strength used for insulation and cooling of a transformer. In liquid filled transformers, dielectric fluid is used to cool the windings and provide optical performance. So in the liquid filled transformers, the dielectric fluid, which is nothing but a liquid, when it is flowing through it, the heat is being taken away by the liquid, thereby it is at normal temperature and gives an optimal performance. It also maintains the insulation of the windings. So sludge formation takes place in the oil due to moisture, dirt or some foreign matter in the oil which is harmful. Sludge formation reduces the rate of heat transfer, ducts are clogged and operating temperature increases. So the oil must undergo dehydration periodically and tested at regular intervals. So these are the few applications of dielectrics where the oil is used, and liquid filled transformers, when the liquid is allowed to pass through it, the liquid is taken away the temperature and the temperature is reduced, thereby cooling effect takes place. So it also maintains the insulation of the windings. Thank you.